All right, we're going to spend some time today going through the trigonometric identities that we learned previously in Honors Algebra 2 and use them to do some evaluating, simplifying, and verifying of other identities. So some of this you might have seen in class already. Different hours got to different places, so if there's something that you just want to skip through, feel free to do that. So take a second to just write these first identities down, things that we've been using throughout Chapter 4 already, the reciprocal identities and the quotient identities. And then we'll jump right into the Pythagorean identities, which hopefully you remember from last year. The first Pythagorean identity is based off of this idea from our unit circle, that if any point on the unit circle, which has a radius of 1, gives us the cosine and sine as the x and y values respectively, then we can form, that's the radius of 1 there, so the hypotenuse is 1, then we can form a right triangle with our reference angle theta and use that idea to know that these sides are the cosine and sine of theta. So we can use the Pythagorean theorem then to say that the cosine squared plus sine squared of that angle theta would equal 1. Now, we're going to use this a lot. This is probably the identity that we use more than any other. We use it in many forms. You do need to just recognize that this leads to these same ideas here, that sine squared would equal 1 minus cosine squared, and that cosine squared would equal 1 minus sine squared. Then we're going to come up with two other Pythagorean identities that can easily be found by manipulating the first one. We're going to first divide that entire identity by cosine squared. If you divide each of those terms by cosine squared, what we get are 1 plus tangent squared equals, and then 1 over cosine squared would be secant squared. So that's our second Pythagorean identity. And again, we're going to need to know this one in a couple of different forms, possibly solve for tangent. So tangent would equal secant squared. Tangent squared would equal secant squared minus 1. And in some cases, possibly, we might need to know that secant squared minus tangent squared would equal 1. Our third identity would come from dividing the first identity by sine squared. If we divide that by sine squared, we're going to have cosine squared over sine squared, which is cotangent squared. And then sine squared over sine squared is 1. And then 1 over sine squared is cosecant squared. So really, what you need to do is memorize this guy right here, which I think is pretty easy to do, and then just know how to get to the other two. You don't have to necessarily memorize those, okay? Nor do you really need to memorize all the other ones that we're writing underneath. You just need to recognize the three major ones in their different forms. So this bottom one here we could rewrite as cotangent squared being equal to cosecant squared minus 1, or possibly the fact that cosecant squared minus cotangent squared would equal 1. All right, so we're going to use these Pythagorean identities quite often. Anytime something is being squared, we have a trig function being squared, there's a good chance, especially right now in this first section, that we're going to be using the Pythagorean identity. The first thing we're going to do is use the identity to evaluate some trig values. In any point going forward in this class, you are not going to be allowed to use triangles to find other trig values. We want you to use the identities instead. So in this problem it says, find sine and cosine if tangent is 5. And then we're also told that cosine is positive. Well, we must be in quadrant 1 if cosine is positive and tangent is positive. So I'm just going to put that right away. We know we're in quadrant 1 because both cosine are positive, and tangent is positive as well. Right? So the first thing that we're going to do is use that tangent value to find another trig value. Well, if I look up here, we know that this is the only one that contains tangent. Okay, so you could start with any of those. The one that would make the most sense is the original one, this one right here, because we can solve for secant squared then, and then secant. So we know that secant squared is going to equal 1 plus tangent squared. Well, tangent squared is 25. So secant squared is 26, which means that secant is going to be the square root of 26. Now in that step, you need to be careful whether or not you'll be using a positive or a negative value. But we've already discussed how this is in quadrant 1, so we must be using we must have a positive secant value then. All right, so we have secant. We can easily find cosine then. Cosine is the reciprocal of secant, so 1 over the square root of 26. Or square root of 26 over 26. All right, so now we have cosine. We're done at that piece. In fact, I'm just going to write that as one of my answers right now. But we also need to find sine. So sine, we can find it a couple different ways. We could use the fact that tangent is sine over cosine, and then solve for sine that way, because we have both tangent and cosine. We could use one of the Pythagorean identities again. We could use the one, the original one, okay, because we could solve for sine pretty easily from that. Actually, the one that we'd be using is that one right there. Why don't we go ahead and do that? We know that sine squared equals 1 minus cosine squared. So sine squared is going to equal 1 minus, well, cosine squared would be 26, square root of 26, square root of 26, over 26 squared, which is, what is 26 squared? Oh, I have it written over here somewhere. 676, I believe. Yep. All right, sorry. 676. So really, we're going to treat that 1 like it's 676 over 676. So we're going to get 650 over 676, and that's what sine squared is equal to, so we're going to need to take the square root of both sides then. So the square root of 676, that's pretty easy. That's 26. And 650, I'm just going to come over here real quick and simplify that radical. 650, we know 25 goes into it. I think it goes in 26 times. And 26 doesn't have any perfect squares in it, so we're good to go there. So this is going to be 5 square roots of 26. That is our sine value. All right, so both are positive. You know, at the end of the problem, kind of make sure that you get your positive negatives correct. We said it's in quadrant 1, so that was a pretty straightforward one. They're both going to be positive. All right, I'm going to put up our cofunction identities kind of all together at once here. I should have this ready to go right away. So if you want to pause the video and then write down the identities in a second here, that's probably going to be the fastest way. All right, so basically what the cofunction identities are telling us are things that we already knew that we used to fill out our trig table pretty quickly. Remember when we said that the sine and cosine of two complementary angles are always equal, right? Well, this is saying the sine of 90 minus an angle, which would be the complement then, would equal the cosine of that angle. So it's the same idea that we used to fill out that trig table pretty quickly. Again, these are pretty easy to memorize. They're all a trig function of pi over 2 minus theta, and it equals a pretty obvious trig function. You know, sine then equals cosine, cosine sine, and then the reciprocals equal each other, and then tangent equals cotangent. So a pretty easy set of identities to memorize. All right, again, we're going to do the odd-even identities here. I'm going to pause it real quick and fill them out, and you can get them down. All right, these are the odd-even identities. I've also heard them referred to as the negative angle identities. Basically, I kind of like this odd-even name because the reason why they are what they are is because some of these functions are odd and some of these functions are even. You know, if you think about the graphs of these, and we've talked about this already early on in this class, we've talked about odd and even functions. The fact that sine is an odd function, okay? It can be reflected over the origin, And when you put, remember in an odd function, when you put negative x into the function, you get the opposite of the original function. Remember odd function, let's write down here, we said f of negative x equaled negative f of x. That's from back in the day, right? Then the other thing we talked about was even functions. When you put negative x in, remember what we got back? We got just the function itself back. So cosine is an even function. Cosine is, cosine is symmetric over the, let's just see if I can do this correctly here, a quick sketch. Cosine is symmetric over the y-axis. All right, so this is not a mistake. There should not be a negative right there. A cosine of negative x should equal cosine of x. Tangent is odd. Remember how tangent graph looks with the asymptotes. Okay, so tangent's an odd function, so it's taking on that property right there. And then the reciprocals just fall in line. All right, so let's take a look at the usefulness of some of these identities here. Some things that we do here are going to be the same as what we did in Algebra 2. Other things that we do are going to be a little bit different. This first thing is a little different. This says find sine of theta minus 2 if cosine is 0.34. And at first you might think, oh, this is going to be easy. We got one of our cofunction identities there. But it's not. If you look back at the cofunction identities, it's pi over 2 minus theta. So we got to do a little work here. What I want you to recognize is, and I think some of you would do this anyways, is if we start with this theta minus pi over 2, we can get this to look like our cofunction identities if we do a little algebraic manipulation here. What I'm going to do is pull out on the inside of that sine function a -1. I'm going to change this to a bracket just to make it look a little more professional. Okay, if we do that, if we pull a -1 out, that theta turns to a negative, and that pi over 2 turns to a positive, so I'm going to flip it around. You can probably already tell where we're headed. Look at how that's already starting to look like the cofunction, except we got that guy right there. We got to take care of that guy. Well, our negative angle identity, our odd even identities said that the sine of a negative angle, so that's basically what this says, there's a negative angle on the inside of that sine, is equal to the opposite of sine of the original angle, so of the pi over 2 minus theta, whatever in that spot right there. So first, from here to here, we just pull out a -1 on the inside. Then from here to here, we used our odd-even angle identities. And now we can replace this. That is equal to cosine of theta, using our cofunction identities. So we know that the opposite of the cosine of theta is equal to, I'll just drop this down, sine of theta minus pi over 2. It's almost like we created our own identity there. That's basically what we did. We're showing that this equals this, and we use identities to prove it. That means that this itself is an identity. It's just not one of our fundamental identities. So what we can do then is say that this must then be equal to, since it says it's equal to negative cosine of theta, negative 0.34. And there's our final answer there. All right, now these are some of the things that we did last year with our trig identities. We did a lot of simplifying, and then we did a lot of verifying as well. We'll do verifying in the next video. So here are some hints. A lot of factoring involved. So remember, factoring, we're always trying to do the GCF first. We'll be using identities to substitute. We'll combine fractions by finding an LCD. And a big one is to get everything in terms of sine and cosine. And that's because all of the identities, all of the trig functions, I should say, can be written somehow in terms of sine and cosine. So if you can do that, then it makes these things easier. You can then have common denominators. You can be able to factor a little bit easier. So that's often a good thing to do. All right, if you look at example 3 here, everything already is in terms of sine and cosine. So what we'll try to do is see if factoring will help us out at all here. There is a GCF that we can pull out. of sine. So I'm going to try that first. Sometimes when you're doing these problems, what you try is not always the best thing. You need to go back to the beginning. That's okay. All right, if I pull out a sine, I get sine squared plus cosine squared. Oh, that's convenient. Sine squared plus cosine squared, I have no idea what I just wrote right there. Sine squared plus cosine squared is 1. So this is sine times 1. I am going to write it just to show that I know what's going on here. And then that just simplifies to the sine of x. That's pretty straightforward. Okay, makes it look really easy, doesn't it? But now if you look back at the original thing, there's a good chance you might stare at that for a while without knowing what to do. That's why we put these hints right here. Okay, try those things. They will work. They help out. There are other things that you could have done there. You could have replaced, since there's a lot of sines and just that one cosine squared right there, another thing you could have done, I actually don't know how far this is going to get us, but another thing, because I don't think I've ever tried this before, you could have done is replaced that cosine squared with 1 minus sine squared. Now everything, oh, this is going to be easy. Now everything is going to be in terms of sine, and then I think intrinsically you would know that it'd be a good idea to distribute that sine through there, and watch what happens here then. Sine cubed plus sine of x minus sine cubed. This is almost as fast as the one that we just did. These two things cancel out, and we're simply left with the sine of x. So there's 2 examples of how we could have done that problem. All right, example 4. Uh, Before we get things in terms of sine and cosine, I put that hint up there, but notice how it's not the first hint, because changing this to 1 over cosine and changing this to 1 over cosine, I don't think is going to get us anywhere to start with here. And I don't think I have this up here. But another good thing to know is, and I'm not going to put it as a hint, but you might just have to do some algebra. Like in this case, we're going to do a little bit of foiling here. I don't know why this is being so goofy right now. I'm sorry. So if you notice, and actually it's related to factoring. Hold on, this thing is not even letting me write out it anymore. I'm going to close it down real quick. Maybe I'll pause the video, fix it. All right, that was painful. I'm sorry. I couldn't close anything down, so you're just going to have to fast forward through that mess. Okay. Uh, let's see here. The first thing we're going to do is FOIL some of this stuff out here. So the numerator, I'm going to rewrite the whole thing to start with here. Secant of x plus secant of x plus 1 times secant of x minus 1 all over sine squared. And then hopefully you notice that numerator is a representation of our difference of squares pattern, that if I multiplied it out, I would get secant squared minus 1, a squared minus b squared. Well, that looks like one of our identities, right? Or looks like it could be, because it's a secant squared. So I'm going to just go back to our identities on the other page here just to see which one's going to be the most useful to me here. This one clearly was secant squared in it. It's probably going to be the most useful, but look at this one right here. Secant squared minus 1 is equal to tangent squared. So what I'm going to do is replace secant squared minus 1 with tangent squared. And then I'm going to put everything in terms of sine and cosine. Tangent squared is sine squared over cosine squared. And this is all over sine. So then I'm going to say that numerator, sine squared over cosine squared, I could multiply, instead of dividing by sine, I could multiply it by its reciprocal, which is 1 over sine. And by its reciprocal, don't use cosecant. We want to keep things in terms of sine and cosine. So what we have here is the sine in the denominator cancels out with one of the signs up there, and we're left with 1 sine over cosine squared. Oh, hold on a second. I was gonna say I think this simplifies more than that. This is a sine squared. Forgot to bring that sine squared along. So this should be squared, and then this entire thing cancels out. So what we're actually left with here is 1 over cosine squared. If you're left with more than one trig function in your problem, um, not that that couldn't happen, but normally this will simplify to one trig value. So this is going to end up becoming, and we don't want fractions in our final answer here, so we're going to get rid of the 1 over and call it just secant squared of x. That's going to be our final answer there. So when I had two functions in my final answer, or when I thought I was going to, that's when I realized something was wrong. So not to say that that couldn't happen, but usually we'll end up with 1 in our final answer. All right, here's our last example here, and we'll shut this video down before it gets too long. It looks like we've got two separate terms here, two fractions. So I think it's going to be a good idea to combine those using a lowest common denominator. So I'm going to just rewrite this problem to start, and then think about what a lowest common denominator would be. Okay, because we always want to have one term in our final answer if we can. So we're going to combine these two fractions together. Well, the LCD would just be the product of the two factors that we see in our denominators right now. So the LCD just would be these two things multiplied by each other. That would be the LCD. So what I'm going to do is multiply this guy by cosine over cosine. I'm going to multiply this guy by the other denominator over itself, 1 minus sine over, I don't really need a parentheses, over 1 minus sine. Okay, and when you do that, be careful with how much you distribute, because we want things to cancel out here too. So this one on the left is going to become cosine squared. I'm actually going to work this way. Is going to become cosine squared in the numerator. Oops. And in the denominator, it's going to be that LCD. So it's going to be cosine of x times 1 minus sine of x. And I'm just going to leave it like that for right now. I'm not going to distribute. I like to keep things factored. In fact, actually, I'm going to combine everything into one fraction right away, so that we have that one denominator here, cosine of x, 1 minus sine of x. And then the other product, multiplying those together, we're going to have sine times 1 minus sine of x. All right, so couple of different routes that we could go here with this. I think I'm going to distribute. I think I am going to distribute that. You could do that right away. I am going to distribute that negative sine of x through and get cosine squared minus sine of x minus sine squared. Actually, it's going to be plus, isn't it? And we are going to then have, let's see down here, we still have cosine of x times 1 minus sine of x. Put an equal sign in there. These two things, I know I can combine together. I forgot my x right there. I can combine together to have a, I feel like I'm missing something here. Combine those together to have 1. I know that that equals 1. Oh, no, I think we're good here. So 1 and then minus the sine of x is what we're going to be left with up on top. Just trying to see if it would cancel out with anything in the denominator. So the cosine squared plus sine squared became 1, and then we also had that minus sine of x right there, which is awesome because in the denominator, okay, don't distribute that denominator out because look at what we have. We have that 1 minus sine of x still. So that can cancel out with that entire factor, and we're left with 1 over cosine of x which is just the secant of x. So we're able to simplify it down into one trig function. Okay, so how do you know when you're done with these things? How do you know what direction to go in? If you follow these hints here, and try to get everything into one trig function and one term if possible, you'll start to see a path as to where you're headed. Like in this one here, I had to stop for a second to kind of see, is this making any sense right here? Obviously these guys can here combine to be one because of the Pythagorean identity, but does it make sense to do that? And then I saw this guy down here and thought, yep, because then they're going to be able to cancel out. So you got to kind of think ahead as you're going too, and kind of tells you where to go. In our next video, we will do 5.1b. So we'll do a little bit of verifying and then maybe some solving as well. A lot of solving.